proving with mathematical induction today. So I hope you're ready for this. Mathematical induction is a mathematical process that we can use to show, a lot of times we can show inequalities. The relationship between them is always true. This is very useful a lot of times for us. A lot of people struggle with mathematical induction because it simultaneously seems extremely difficult and extremely trivial. And we're going to kind of address some of that. It's mainly, this video is about the mechanical aspects of using mathematical induction as opposed to the theory behind it. A brief overview on the theory is we're going to show case one, meaning we're going to show this simple case, maybe multiple cases sometimes, where it's true for one or two, normally just one iteration of a particular value. So we know that it actually does work sometimes. And then we're going to assume it to be true generally. And then we're going to prove that that general case is true plus 1. So we're going to show that general plus 1 is also always true. Now, sometimes people really struggle with this idea of, well, we're going to assume it to be true. Isn't that just kind of assuming to be true what we want to prove to be true? Yes, but no. We're going to assume the general case is true. What we're doing is starting with a premise. And we want to show that premise is true. So the idea being, if the premise was false, when we do the plus 1 case, plus 1 case is going to fall apart. It's going to show it's false. But if the plus 1 case was true, it meant that the premise was true. So we're starting with an assumption. We're going to work out forwards. And if we end up with a false statement at the end, it meant that the original statement we started with was wrong. So the second part here will be taken care of by the third part. If the third part works out to be true, 2 is true. If the third part is false, then the second part was also false. And that's basic logic right there, is the idea of P implies Q. Okay? So that is the idea. Assume this, then Q has to be true. If Q is true, that meant that P had to be false as well. Pardon me, if Q is false, that meant that P had to be false. So I have an example for us to work out. And here we're talking about a geometric sequence is less than a factorial sequence. That's the general idea of what we're looking at here. And that's always going to be true. Factorials are always going to grow larger long term than exponentials and most other functions as well, or sequences. So let's start with case 1. So case 1 is simple, right? So part 1, you can do this A, B, or C. I do 1 to circles. Part 1, we're going to say let n equal, and notice here it starts at 0, right? So what I'm talking about, let me back up and give you some of the terminology in case you don't know this. Upside down A means for all, or for, well, that's what we'll stick with. For all n belonging to the set of integers. This E-looking thing is a symbol, mathematical symbol for belonging to. So for all the values of n belonging to the integers that happen to be greater than or equal to 0, can't really see that very well, but there's a line there, so greater than or equal to 0, 2 to the n power is less than n plus 2 factorial. So let's let n equal to 0. This is our primary case here. So we get 2 to the 0 less than 0 plus 2, right? 2 to the 0 is 1. 0 plus 2 is going to be 2 factorial, which is just 2, so 1 is less than 2. So that piece checks out. So the primary case is true. Part 2, all right? Part 2 is assume the general case. So assume that 2n is less than n plus 2 factorial. Okay, and that's a little bit off the board. Sorry about that. Okay. Now, we want to prove that 2n plus 1 is less than or equal to 2n plus 3. All right, and if you're struggling with that, pause for a second, just kind of think this through. But I'm doing n plus 1, the next case, right after the general one, right? So I'm doing n plus 1. So I'm taking n, I'm doing n plus 1, I'm taking n plus 1, so it becomes n plus 1 plus 2, which becomes n plus 3. I want to prove that. Where am I going to start? Well, I assumed I have something that's true, right? So I have 2n to the n is less than n plus 2 factorial. That's something I know or I'm assuming to be true. keeping in mind that anything I do after this will fall apart if this initial statement was false. So I'm going to do this. I'm going to multiply both sides by 2. Okay? So I'm going to come along and I'm going to do multiply by 2. So I get 2 to the 2 times 2 to the n is less than 2 times n plus 2 factorial. This is 2 to the n plus 1, right? Now what? This is where we're like, well, how do we deal with this, right? Now, this is a thing where we have to go back and we have to remember something. N is greater than or equal to 0, right? N is greater than or equal to 0. So a piece that we need to note here is that we know that 2 is going to be less than n plus 3 for all values of n. Because when n equals 0, right? When n equals 0, that's 0 plus 3, which is still greater than 2. So from the very beginning, we know that n plus 3 is going to be larger than 2 for all values of n. Okay? So that's true. So that means that 2 times n plus 2 factorial is going to have to be smaller or less than n plus 3 times n plus 2 factorial. Right? Now, if that was a jump, you're like, where did that come from? Remember, it's an inequality, right? So 2 is less than n plus 3, so here's the 2. I'm replacing the 2 right here with n plus 3 right there. And now I have this inequality going on. So now I know that n plus 3 factorial is larger than this thing. And I knew this was larger than 2n plus 1. Look at that. You got it. All right? You normally end a proof with some type of notation, just like you would with a sentence with a period or something like that. Standard mathematical notation is QED, which is Latin for was asked to be shown, or a lot of modern texts will use a square with a filled-in square right there. A lot of times I just write BAM because it's a little bit more fun. But anyway, doesn't matter as long as you denote it as something has happened there. So here we showed that this statement is always true through mathematical induction, and this is how we got there. Okay, so I encourage you to rework this problem by yourself. Come back and rewatch the video. Make sure you understand what's going on, and enjoy math. All right, and see what else you can use mathematical induction with. It's kind of cool. Take care.